Welcome. In this session in linear data analysis, we'll explore the receiver operator characteristic, or ROC curve, for a fictitious example. Suppose that there's a virus that's going through a population and that it has two genetic variants. We can detect the virus through a very fast, inexpensive test, but determining which variant a patient has requires a long and expensive laboratory test. So suppose that we know from studying this laboratory test in a population that what we see is that it promptly infects people. That is, this is the percentage of the affected population over the number of days. So by the time 4 days have passed, that's the peak of the infection for most people. And then the number of, by the time we've reached 10, everybody who's going to get infected has been infected. Now suppose that variant 2, which has a different genetic makeup from the same virus, infects most people, but it does so slowly and eventually. So it takes 7 or 8 days for this to have reached its peak infection rate. And then it's only after 20 days past the suspected time of infection that we can determine that, that this has basically faded out. So the question is, without going through these expensive laboratory tests, can we use the inexpensive test plus the number of days that have elapsed to determine whether people have variant 1 or variant 2, and then we can give them the most appropriate therapy for the variant of the virus that they have. So that's the setup that we want to explore. Now, when we're doing this, what we're really looking at is we're looking at the cumulative detection, which is the area under the curve, and our hyperparameter, theta, is the number of days from the onset of the infection. So for example, suppose that we have our inexpensive test, and after 2 days we detect a certain number of people who are showing positive, and we don't know whether they have variant 1 or variant 2. The area under the red curve will be our true positives. That is, those are the people who have the variant 1 virus. And then the area under the other curve will be the false positives. These will be the people who are showing positive, but they actually don't have variant 1, they have variant 2. And as we proceed through the number of days, the relative number of people who have variant 1 or have variant 2 will change. And so we'll detect an absolute difference in the number of people who are infected based on our fast test, and what's underlying that we can't get at directly is whether they have variant 1 or variant 2, and whether we should be giving them one therapy versus another therapy. And so for each value of this hyperparameter, what we can do is we can build the number of true positives and the number of false positives, and then we can start looking at those, and we can build an ROC curve for the hyperparameter being the number of days from the onset. So let's take a look at what this would do. We would vary this hyperparameter from 0 to the maximum number of days we think this inexpensive diagnostic test is useful, and that would be 20. So for a small, for this small value of the threshold, here's our false positive rate. That is, we start out with a 0 false positive rate, and then as we accumulate, we're getting an increasing number of false positives. Here is our true positive rate, and this represents our fast variant. So we're very quickly getting a number of true positives, and along the way we're picking up a number of false positives. Now it's possible to interpret these curves. For example, we can make an immediate observation, which is that for this data the false positive rate is always less than the true positive rate. But how can we get a sense of the performance of using the number of days to shunt people into one therapy or another? Well, that's where we use the ROC curve. So now our independent variable is the number of days post-infection, and the false positive rate and the true positive rate are now dependent. That is, For a given theta, we can compute the areas underneath these incidence curves, and we can then compute the confusion matrix, and from the confusion matrix come these two values, and from those two values come an ROC point. And what we find is this, is that 2 days post-infection, the false positive rate is quite small. The true positive rate is also not very large. By the time we get to 4 days, we have a false positive rate of less than 20%, and our true positive rate is up to over 50%. As we increase the number of days, our true positive rate is rising, but so is our false positive rate. And as we proceed, we eventually have captured the entire population. So the area under this curve is one measure of the overall performance of using the number of days post-infection to decide whether a person gets the therapy for variant 1 or the therapy for variant 2. Ideally, this curve would shoot up here and then flatten out. That is, we would love to find a way to determine that has a low false positive rate and a very high true positive rate. As it happens, for this particular data, the duration since the onset of the infection is not a particularly useful one. The null hypothesis would be that the false positive rate and true positive rate increase linearly, that is, they are exactly balanced. Here, when I perform an area under curve calculation, I get 0.86. It would be 0.5 if we were operating with the null hypothesis, which is basically if we were going by chance, and it would be maximum 1 because a unit square has a maximum area of 1. So the area under the curve is going to be bounded typically between 1/2, which is the area under the chance or null hypothesis curve, and 1, which is a perfect classifier. Here we find that the area under the curve is 0.86. What this suggests is that for this virus with these variants, using this rapid diagnostic test, that shunting people into one therapy or another based on the time is not ideal. In this lecture, we've gone through the confusion matrix, both in its absolute and in its relative form. The key measures for the confusion matrix are the false positive rate and the true positive rate. This leaves us with a 2x2 relative confusion matrix that only has 2 degrees of freedom. These 2 degrees of freedom can be plotted as the ROC curve, and as we change a hyperparameter, such as the threshold of a score, we can see how the ROC changes with this hyperparameter change. And the area under the curve gives us the improvement of our method over the null hypothesis. So we're now able to compute a relative confusion matrix. We can find the ROC point for a confusion matrix. We can plot the curve for a hyperparameter, and we can assess the curve using the area under the curve measure.